IBM just fit 100 billion transistors onto a chip the size of your fingernail. That's roughly 12 transistors for every human being on Earth, crammed into a piece of silicon smaller than a grain of rice. And the timing could not be worse for China. Here's why. Every video on this channel about China's chip race has been about closing a gap. EUV, DUV, memory, optics, all of it framed around catching up to where the leaders currently stand. IBM just moved the finish line again. Not gradually. Overnight. Stay with me, because there's a number about 90 seconds from now that explains exactly how IBM pulled this off without shrinking a single transistor smaller than before. And it's the part almost nobody covering this story explains correctly. A quick word on sourcing before we go further, because a claim this big deserves it. Everything in this video comes from IBM's own research announcement, Reuters, MIT Technology Review, and independent semiconductor analysts who reviewed the actual VLSI presentation. Nothing here is speculation dressed up as fact. Here's what actually happened. On June 25th of this year, IBM unveiled what it calls Nano Stack, a chip architecture built around a 0.7 nanometer transistor node, also called 7 angstroms. It's the world's first sub-1 nanometer chip technology, and IBM didn't just publish a paper about it. They built an actual working test chip and showed it off at the VLSI 2026 symposium in front of the entire semiconductor industry. 100 billion transistors on a fingernail. Let that number sit for a second before we go further. For comparison, IBM's own previous flagship, a 2-nanometer chip unveiled back in 2021, packed roughly half that density. Nanostack didn't inch forward. It nearly doubled the entire benchmark in a single announcement. So here's the twist, and it's the part that makes this genuinely different from the usual smaller is better chip story. IBM didn't get here by shrinking transistors sideways, the way the industry has for 50 straight years. They stacked them vertically instead, in 3 dimensions, using ultra-thin nanosheets, just 15 atomic layers thick. Instead of packing transistors tighter across a flat surface, Nano Stack builds upward, adding a second layer directly on top of the first. Think of it like a city that ran out of room to expand outward, so it started building skyscrapers instead. Same land. Twice the space. IBM just did that to a transistor. 50 years of chip-making history, and the industry essentially just discovered it had a second dimension available all along. Here's the re-hook, because the number that comes next is the one every headline about this story gets wrong. IBM claims Nanostack delivers up to 50% more performance and up to 70% better energy efficiency compared to its previous 2-nanometer design. Read that gap again. 50% faster, 70% more efficient. Those aren't small incremental upgrades. Those are the kind of numbers that used to take an entire industry 3 or 4 node generations to achieve. 3 or 4 generations of progress, compressed into one announcement. That's the number that should make every competitor in this industry pay attention, regardless of what happens with manufacturing. But here's the sentence that should stop you before you get too excited. IBM doesn't actually manufacture chips at commercial volume anymore. Sit with that, because it changes everything about how you should read this announcement. IBM licenses its chip architectures to the companies that actually build them: Samsung, Intel, and specifically Japan's Rapidus, which is already using IBM-derived technology in its own 2-nanometer push. As of this announcement, IBM has not named a manufacturing partner for Nanostack at all. That's not a small footnote. That's the entire ballgame. A blueprint isn't a building. Somebody still has to pour the concrete. Here's why history matters so much here. And it's the rehook that should genuinely worry you if you're excited about this timeline. IBM unveiled its 2-nanometer chip technology back in 2021. 5 years later, in 2026, that exact technology is only now approaching real volume production, largely through Rapidus in Japan. 5 years, from announcement to anything resembling commercial reality. IBM itself says production for Nano Stack is at least 5 years out, and given their own track record, treat that as a floor, not a ceiling. 5 years for the last one. At least 5 years promised for this one. IBM's own history is quietly telling you how to read its own headline. TSMC, meanwhile, isn't standing still waiting for IBM's research to mature. TSMC began volume production of its 2-nanometer N2 process back in the fourth quarter of 2025 and is already ramping capacity toward 100,000 wafers a month this year. Apple alone has locked up more than half of TSMC's initial 2-nanometer capacity for upcoming chips. TSMC's enhanced N2P node ships in the second half of this year, and its next major leap, a 1.4-nanometer node called A14, is already targeted for some time after 2027. While IBM was showing off a research chip in a conference hall, TSMC was shipping 100,000 real wafers a month to real customers. So here's the honest scorecard, because the title of this video makes a claim that deserves real scrutiny. Does this make TSMC obsolete? No, not even close, not on any timeline that matters in the next 5 years. What it does is prove that a completely different path forward exists, vertical stacking instead of lateral shrinking, at a moment when lateral shrinking was genuinely starting to run into real physical limits. That's a legitimate, important research milestone. It is not a product anyone can buy, license into a real factory, or ship inside a phone anytime soon. A research breakthrough and a shipping product are two different milestones wearing the same headline. There's also an honest caveat buried inside the numbers themselves that most coverage skips entirely. A label like 0.7 nanometers isn't a literal ruler measurement anymore. IBM itself acknowledges these node names describe a generation of manufacturing technology, not the actual physical size of anything on the chip. What's concrete is the transistor count and the density. The number in the name is closer to marketing than measurement, and it has been for years across the entire industry, not just IBM. Now here's the rehook that actually connects this back to everything this channel has been covering about China. While Beijing has spent years and tens of billions of dollars racing to build a domestic EUV machine just to reach the 2-nanometer tier TSMC already mass produces today, IBM just demonstrated a credible path to something beyond 2 nanometers that doesn't even require shrinking transistors laterally at all. That's not China falling further behind because of anything China did wrong. That's the finish line accelerating away from everyone chasing it, including China, at the exact moment multiple Chinese labs were finally closing the gap on today's generation of tools. Remember the moving finish line problem from earlier videos on this channel. This is that problem in real time, with a specific date attached to it. China's factory floor EUV prototype is racing to reach where TSMC already stands. IBM just proved TSMC itself has somewhere further to go. It's worth being fair here too, because China isn't the only one facing this exact squeeze. Intel and Samsung are both pursuing their own versions of three-dimensional transistor stacking, chasing the same underlying physics IBM just demonstrated, and neither of them has publicly shown a working test chip at this density yet, either. IBM's announcement resets the clock for the entire industry, not just for the country furthest behind. The difference is that Intel and Samsung already mass-produce chips at the current cutting edge, giving them a running start China simply doesn't have. China isn't just chasing the next generation. It's still finishing the lap everyone else completed years ago. Here's the technical detail worth understanding before we close, because it explains why nobody solved this sooner. Stacking transistors vertically sounds simple in theory. Just build a second floor on top of the first one. In practice, it requires aligning two layers of circuitry with atomic-level precision, since even a tiny misalignment between the top and bottom transistor layers ruins the entire chip's performance. IBM's specific breakthrough wasn't the idea of stacking itself. Other labs have tried versions of that for years. It was finding a manufacturing method precise enough to actually align those layers reliably, which is exactly the kind of unglamorous, expensive engineering problem that separates a concept sketch from a working test chip. IBM's near-term focus, according to the company's own chief scientist Dario Gil, isn't commercializing Nano Stack immediately. It's helping existing partners scale today's 2-nanometer nanosheet technology, the same underlying architecture family IBM pioneered and licensed to Rapidus, Samsung, and eventually others. Nano Stack is the roadmap beyond that, not a replacement for it starting tomorrow. Translation: the thing everyone's excited about isn't even IBM's actual priority right now. Watch whether IBM actually names a manufacturing partner for Nano Stack within the next year, because that single announcement would do more to validate this technology than any transistor count or efficiency percentage in today's presentation. Watch Rapidus specifically, since Japan's entire national chip strategy is built around eventually absorbing exactly this kind of IBM-originated technology, the same way it's currently absorbing IBM's 2-nanometer work. And watch TSMC's own roadmap past A14, because the real question isn't whether Nano Stack works in a lab. It's whether TSMC, Samsung, or Intel gets there first, using their own competing three-dimensional stacking research, something all three companies are already independently pursuing. There's one more layer to this worth understanding: the strategic question of why IBM chose to make this announcement now, in public, at a symposium, instead of quietly developing it further behind closed doors. IBM stopped manufacturing its own chips years ago, which means its entire business model in this space depends on convincing the industry and investors that its research division still sets the pace everyone else follows. A splashy, headline-grabbing demonstration, even one that won't ship for half a decade, is exactly the kind of move a company makes when it needs the world watching its research pipeline closely, not quietly ignoring it in favor of TSMC's latest wafer shipment numbers. That doesn't make the science any less real. It does mean the timing of the announcement itself was a calculated business decision, not just a scientific milestone that happened to land on a random Thursday. Intel is worth mentioning here too, because it's chasing this extreme transition from a very different starting position. Intel's own roadmap includes an 18-angstrom node already shipping in limited volume, with a 14-angstrom generation targeted for later this decade, explicitly built around similar backside power delivery and eventual stacking concepts. Unlike IBM, Intel still operates its own fabs, which means whatever Intel builds, it can actually manufacture without waiting on a licensing partner. That single difference, owning the factory versus renting out the blueprint, is arguably the biggest structural advantage separating IBM's Nano Stack announcement from something Intel or TSMC eventually ships themselves. There's a broader pattern worth naming here too, one that applies to the entire chip industry right now, not just this one announcement. For 50 years, progress meant making transistors smaller. That approach is running into real physical limits. Atoms don't shrink forever, and every major player in this industry, IBM, TSMC, Intel, Samsung, and yes, China's own research labs, is now racing toward the same next chapter, stacking transistors vertically instead of squeezing them tighter. Nobody has fully solved that transition yet. IBM just published the most credible early proof that it's possible at all. Markets noticed immediately, too. IBM shares jumped more than 6% in pre-market trading the morning of the announcement, even though the company has fallen roughly 11% so far this year. Investors weren't pricing in a product they could buy next quarter. They were pricing in a company that just proved it still has a credible seat at the table in a race everyone assumed TSMC, Samsung, and Intel had already locked down between themselves. Here's why this actually matters beyond a research headline, too. Every AI data center running today burns an enormous amount of electricity, and a huge share of that power goes toward exactly the kind of computation Nanostack claims to make dramatically more efficient. A 70% efficiency gain, if it ever reaches real chips, doesn't just mean faster phones. It means AI companies training massive models could eventually do it using a fraction of the electricity they burn today, which changes the economics of the entire AI industry, not just the chip industry sitting underneath it. If breaking down what these announcements actually mean, instead of repeating the headline that made TSMC sound obsolete overnight, is what you want more of, that's exactly why subscribing now matters, because I'm tracking every one of these announcements as they land, including whichever Chinese lab responds to this exact challenge next. This isn't the last time a Western lab is going to publish something that resets the timeline for everyone chasing the current generation of chips. And I want you seeing that story the moment it breaks, not weeks after everyone else has already picked it apart. And if you want to see exactly how far behind China's own chip-making equipment still is on today's generation of tools, the gap this exact announcement just made even wider, the video on your screen right now walks through precisely that gap. Click it before you go anywhere else. Drop one word before you do. Leap, if you think Nanostack genuinely represents the next real chapter of chip design, worth the hype. Lag, if you think a 5-year-plus timeline with no manufacturing partner means this headline got way ahead of the actual science. Type it now, then go watch that video, because the gap it explains is about to get even harder to close.